Well, here we are at class number 17. This is unit number 3, emissions, perspective, and firing defects. So this is the final class in the course on firing of ceramics. So unit 3 is essentially just a single class. But when I designed the course in the beginning, I didn't know that I'd be able to put all these thoughts into one class. So I have. So let's get about talking about kill emissions and firing defects. So in particular, I want to talk about species in the kill exhaust. Usually we talk about these as emissions in the kill stack gases. And of course, they originate from the combustion of fuels. That's one place where we get species, chemical species, compounds in the stack gases and elements, particulate matter, whatever it may be. And we also have these originate from reactions and processes within the load during sintering. So there are two sources of these species, the combustion and the load. This class just seeks to help you put these things in perspective, because a lot of people think that if there is a species that could be harmful to somebody's health in a kill exhaust, then it's terrible. Well, of course, one of the things I learned in all of my career was human beings have a dose and response reaction to chemical elements and chemical compounds. Here's an example. Vitamins sometimes contain selenium. Selenium is a good trace amount substance in a vitamin for older people, particularly males. But selenium is also poisonous. And so in higher concentration, it becomes poisonous. So some things that are in kill emissions in firing ceramics are perhaps helpful to the environment, not harmful, and some might be harmful to the environment. So I want you to keep an open mind about what we talk about today, and I want to give you all my perspectives on this. Now, what is clean air? That's the first starting point, and in the United States, we have clean air defined by something called the National Ambient Air Quality Standards. You have similar standards in Europe. So in our country, we have standards for all the substances that you see listed here. Now, the National Ambient Air Quality Standards considers all of these substances on this list to be what are called criteria pollutants. They're the ones that can have a long-term effect on human health. So over a lifetime of exposure, you shouldn't be exposed to more than these particular limits that are given here in the chart. So carbon monoxide, obviously a poisonous gas. At low concentrations, you can be exposed to 9 parts per million. And shorter exposures, as much as 35 parts per million. Above that, it can have a very detrimental effect on human health. Nitrogen oxides, all of these terms, pollution measurements usually involve NOx, NOx as NO2, the compound. Lead, an obvious substance that can affect human health. There's a lot of lead in the environment, and so nevertheless, it's listed here. PM10. Okay, we've talked about particulate matter with an average size less than 10 microns. In this particular case, if the particles are less than 10 microns, then they can make it into the lungs. They're not caught by the nose and throat of a human being. They can make it into the lungs, and therefore they can be dangerous. our regulatory people also define something called PM 2.5, 2.5 microns, and they consider those to be fine particles. Not me. I consider fine particles to be those that pass through a fabric filter, which means that they're usually about a micron in size. It turns out our regulatory people figured out that they could only measure particles as small as 2.5 microns with the equipment they had without spending a lot of money. So they said, okay, we're going to have a cutoff at 2.5 microns, not a micron. Ozone, O3, you can see that we have limits on ozone at the surface of the Earth. We're not talking about stratospheric ozone. At the surface of the Earth, ozone can burn people's lungs, for example. So therefore, sensitive people have to be very careful about exposure to ozone. Ozone is very useful in the environment, by the way. Of course, it's nature's disinfectant. So it's out there. It's created by the action of sunlight on certain tree resins that may be emitted and can be fairly high in forest locations where there are a lot of pine trees. And then, of course, sulfur dioxide. So those are the substances that are listed. And if you're below those limits, then you are in compliance in your area of the country. If you're above those limits, as we are in the United States, then certain areas, particularly around cities, because of the automotive pollution from gas engines, then we're going to be not in compliance, meaning we don't have clean air in those areas, as defined by the United States Environmental Protection Agency. So those are the long-term exposures limits. We also have short-term exposure limits, and in the United States, we call those the hazardous air pollutants. Hazardous air pollutants, or HAPs. The substances on that list is quite a long list, but pertinent to ceramic manufacturing are hydrofluoric acid, HF, and hydrochloric acid, HCl. Originally, in the legislation that was approved in our country, particulate matter was not a HAP, but the environmental agency said that since there are some materials in particulate matter that contribute to human toxicity, that are toxic, then we need to include all particulate matter. So therefore, they're regulating HAPs. Whether that was the intent of lawmakers or not, you can be the judge. I don't think so. But okay, so if you take the criteria pollutants and the hazardous air pollutants, which are intended to, the latter, these hazardous air pollutants intended to express short-term exposure conditions that may affect human health, then that's what how we define clean air, and that is what clean air is defined around a ceramic manufacturing facility in the United States. I think you can use that same line of thinking with your regulations in other countries as well. Okay, so of course we have emissions from combustion and emissions from the load. So when I was a sophomore, I thought that you took natural gas, reacted it with oxygen or air, and you ended up with water vapor and carbon dioxide, and that's about it. Of course, the nitrogen came along for the ride, and if we're at low enough temperatures, we don't have nitrogen oxides formed in combustion. That's what I thought. That was wrong. You saw this diagram in the last class, and remember that these predictions are from a steady state model. Maybe a few of you will recall that we talked about the fact that we don't do calculation of adiabatic flame temperatures in combustion anymore, but that's taking each combustible species and reacting with oxygen and looking at the reaction products. That's the theoretical or ideal world. That's not exactly the way it is. So last time you saw that this particular slide. This slide was the verification model where we were doing a laboratory firing in order to verify the amount of gas that was used. So we had a heating schedule in our Swindell kiln. The Kiltel gave us the oxygen, and you'll recall that we had a lot more oxygen in the exhaust than we expected. We certainly weren't on ratio. Ratio would have been 2% oxygen, and it would have gone like this, but it didn't. And the reason is, in the early stages of combustion, we just don't have equilibrium conditions. The Kiltel also gave us the carbon monoxide emissions, and you can see they are increasing as the kiln is heating up. The Kiltel gave us the carbon dioxide emissions as well as the green line. And we get up to a certain temperature and the carbon monoxide really took a dive here and went very low. That's because we got to the auto ignition temperature of carbon monoxide. So it started reacting with the oxygen in the kiln environment and burning to give carbon dioxide. Nevertheless, that's what happened right here. But you can see from this that heating up the kiln, there's some species we didn't expect, like carbon monoxide. We did not think that's going to happen. So, of course, in burning out binders, you can produce carbon monoxide. In combustion systems that aren't properly adjusted in air to fuel ratio, you can have carbon monoxide. So, or reduction firing, as you might call it. So, nevertheless, the real world is a little bit different than the ideal calculated world. Okay, we'll move the window back to where you can see everything. So it's not just as simple as methane plus oxygen giving us carbon dioxide and water. What about CO? We just talked about. What about soot? Soot is a product of combustion. And you can believe it if you look on the inside of your exhaust outlet on your gasoline or diesel powered vehicle, if you still have one of those. I don't think we all have electric vehicles just yet. And so you can see soot, carbon particles that are produced by combustion, particularly in reduction firing in a kiln. That means oxygen deficient firing. We're going to produce soot in the kiln, and it can be an emission. What about unburned fuel? Can that pass through the kiln? How about molecular fragments from incomplete combustion of complex fuels like propane or fuel oils? Can some combustion take place, but we get these fragments of partial molecules being floating around in the kiln atmosphere? And what about reactions between nitrogen and oxygen? And so there's a little definition of atmospheric NOx here that came from Wikipedia, and you can see that NOx is NO and NO2 taken together. That's why our environmental agency regulated NO2. That's total NOx expressed as if it were all NO2. Well, here's a little definition of soot from Wikipedia. Soot particles being submicron typically in size, and carbon, they're going to pass right through fabric filters and not be captured and enter into the environment. Now, of course, those particles can be considered hazardous to human health because they're carbon. They may have hydrocarbons attached to their surface. That's one reason that smoking is so dangerous to human health. You're inhaling particles because you're living on the face of the earth, and some of the smoke is condensing on the surface of those particles. It makes it a more difficult situation for your health and in your lungs. So NOx, what temperature is NOx formed? And you can see that in this quote, NOx is formed about 2,800 degrees Fahrenheit. That's above about 1538 degrees Celsius. So most natural gas burners can produce NOx. It's not from the nitrogen in your product, primarily, but it's from the high temperature burners. One very practical way to look at this is if your kiln is fired above 2,800 degrees Fahrenheit, then you're going to have a situation where the air passing down or through the kiln can create NOx. Now we have low NOx burners today. Your burner supplier can help you reduce the NOx emissions, which in non-attainment areas in the United States is a very important thing in ceramic manufacturing. Now I went some trouble in one of my classes to estimate the soot from natural gas combustion. So I took the EPA emission factors for total suspended particulate matter and the AP 42 chapter on natural gas combustion. And that's the number I got, 0.0076 pounds per million BTU. And I subtracted out the filterable particulate matter. That's what the fabric filter would scrub out of the gas. And so you can then say the soot's the balance. That's about 75% of the suspended particulate matter in natural gas combustion. Okay. Well, I hope that's given you some insight into what happens from combustion. It gets more interesting when you use more complex fuels, long-chain hydrocarbons like propane, or certainly fuel oil in combustion, any type of oil. So the emissions really boil down to things that are in the National Ambient Air Quality Standards, the criteria pollutants. The HAP list, like the hydrogen chloride, hydrogen chloride, hydrochloric acid, some carbon emissions can be really important in parts of the world and should be important here in the United States, perhaps. Right now, we're trying to rejoin the global warming treaties of the world, and perhaps that will happen. Particulate matter and condensable particulate matter. So condensable particulate matter is something that was liquid at the stack exhaust temperatures, but as the stack plume cools, that condenses into a solid substance. So particulate matter comes from dust or silica, anything that is in the plant environment that's taken through the combustion system, because as you know, some dust is going to make it into the burners. It's from dust that's coming down the tunnel with the excess air in the tunnel. If it's a tunnel kiln, it's dust shaking off the product. It's condensable particulate matter from whatever's happening within the kiln. We have volatile organic compounds, and those can be molecular fragments and compounds that evaporate. And then metals, species that are emitted from the kiln as metals. And those include things like iron and manganese and chromium, which can be important in ceramic manufacturing. So we're going to start with removal of the binder in ceramics. And here, Professor Reed, in his wonderful book, Principles of Ceramic Processing, has given us a chapter which talks about removal of binders, including polyvinyl alcohol, PVA, methyl cellulose, acrylic binders, polyethylene glycol. So many of these things will break apart and depolymerize, break into molecular fragments at certain temperatures, and might depend on fast heating or slow heating. But that's one source of binders. Now remember that binder removal is going to create gaseous species of some sort, which is going to create an internal pressure within the ceramic. And done too fast, that can cause some cracking in the ceramic. Now, of course, a lot of the natural carbon in our materials is removed by oxidation. So there's a piece of brick with what's called the black core. That black area is not carbon, okay? It's what you really think should be carbon because we didn't burn all the carbon out of this brick on heating. So when you look at the carbon content in the surface compared to the core, they're within experimental error the same. If you look at the mineralogy of the product, the red areas, quartz and mullite and hematite, red iron oxide, Fe2O3. So if you chisel out the core area, you can find mullite. Well, that's what we expect, but now we found a different spinel called hercynite. Hercynite is a black colored mixture of magnetite and iron spinel minerals. And so this is not carbon right here. It's the effect of carbon reducing the iron oxide to magnetic iron oxide or magnetite, which in firing a brick becomes part of this complex spinel called hercynite. Now this is normal and this is okay. So I'm going to tell you a couple of stories about it. Here's the first story. One time I wrote a little paper for a roofing tile manufacturer in California. Roofing tiles typically contain a black core. Okay, and the standards for manufacturing roofing tiles say a black core is okay. It reduces some of the iron oxide, makes more glass, makes a stronger and lower water absorption roofing tile. All that's good. But somebody wrote the president of my university and said I was defrauding the people of California by making these statements that a black core was not okay. It was a defect in the ceramic. So I got a call from the president's office and they said, Dr. Brosnan, get up here. You got to explain to the president why you're not defrauding the people of California. So I had to go into the president's office and explain to him what a black core was. I don't think he ever really grasped it. But then I said, well, the ASTM standard for roofing tile allows a black core, and therefore it's okay in a roofing tile product. And right there he said, oh, okay, you're not in trouble. That's a good thing, being a professor, to be not in trouble. However, I did get a memo from the legal a little bit later on saying, from now on, when you write something like this, you got to put a disclaimer into each particular writing saying this is your opinion and not the university's, because we don't want to get sued. You can get sued. Okay. Here's another story. Recently, I was contacted by a guy who bought some bricks in the UK, and he said they're cored, and therefore I don't think they're good. What do you think? Are they good brick or not? And I wrote back and said, any brick that meets your national product standards is what a good brick is. Okay, if these meet national product standards, they're okay. They're a good brick. Now, I further said that very clearly, if you don't see any cracks around the core, okay, if you have cracking around the core, then that could be a bad thing. But if you don't see any cracks on any of the cut surfaces where you see the core, broken surfaces, then the bricks are okay. I don't think that's the answer he wanted. I think it was the answer the brick manufacturer probably wanted. My comments were really designed to be an impartial observer. And so that's why I said anything that meets product standards in your country means it's a good brick. Okay. Now to some emissions like hydrogen fluoride emissions. I want to tell you something about hydrogen fluoride. It's well documented in human health literature that hydrogen fluoride exposures over a long term cause developmental difficulties, particularly in children. Okay, it causes abnormal bone growth as humans develop, as they age, and causes real problems with children. And that was discovered by people in societies that were not advanced, that were living in very small enclosures, you might call them huts, and they were burning coal within the enclosure, and the coal was releasing hydrogen fluoride. So they had long-term exposures, and that caused this developmental difficulty. Well, I understand that. Okay. Also understand that there's fluorine in the toothpaste that I use to clean my teeth, and there's no prohibition on me using a fluorine toothpaste every day and rinsing it, and that goes down the drain in my house. So what's the deal here? Well, again, it's this dose and response idea. A long-term large dose can be bad for a human being. A short-term low dose can be not so bad. So in ceramic manufacturing, if you're using a clay raw material, fluorine is part of the clay crystal structure, a very small part. It turns out that fluorine is about the same diameter and about the same charge as an hydroxyl ion, an OH. And therefore it substitutes for some hydroxyls, a few hydroxyls in the clay crystal structure, because clay was always in the environment when the clay was created. Well, when you fire the clay and go through dehydroxylation, and the hydroxyls come out, if fluorine is present, it's going to come out too as a fluorine F- ion. But it can't stick around as fluorine very often because fluorine is so reactive, so it grabs the hydrogen from somewhere and becomes a molecule of hydrogen fluoride in the kill exhaust. So first of all, you're going to have dehydroxylation temperatures in order for the fluorine to be released. I got a little discussion with an environmental regulator one time, and he said a company was emitting fluorine in their clay mining area, their clay pit. Fluorine was being emitted. And I said, that's ridiculous. Okay, you got to heat the clay up in order for dehydroxylation to take place, in order for the fluorine to be released. What the company is emitting is clay dust, dirt particles, not fluorine. And the environmental person said, well, if fluorine is in the clay dust, then it's a fluorine emission. Well, I don't agree, because the response in human health to clay dust is a lot different than the response to hydrogen fluoride. So sometimes my opinion is that some regulators can lose perspective. Now, fluorine is released on heating in a tunnel kill. It can condense on water molecules in the kill exhaust as the draft goes toward the smokestack, and the heat that's present can release it at lower temperatures. So we get a continuous fluorine cycle in the cooling section of the kill. Evaporation, condensation keeps happening. And whenever you have that kind of cycle in the dynamic process, occasionally the kill is going to put out a spike of hydrogen fluoride. That has happened. In my laboratory, we can heat the clay sample in the simultaneous thermal analyzer, which gives the thermogravimetric axis here. The green line is the clay was heated up, and as you can see, once we got up to about 500 degrees C, we started losing weight. And HF is the red line over here. Here's the HF scale. And well, when the water was evaporating, we got a little bit of HF. Also use lab tempering water here, city water, in this experiment. But nevertheless, you can see that we got a lot more HF as we went up in temperature to dehydroxylation. It turns out the clay hangs on to some of the HF, and it doesn't come out till you get up more toward the soak temperature of the kiln. Now, this particular clay sample had some sulfur dioxide emissions as well. We're going to talk about that in just a minute. So, okay, so what you've seen is that the spike in HF is when we have dehydroxylation. Some of the product holds on to some of the HF that comes off later in the process, okay, later in the process. So there are two periods of HF evolution, both in preheat and both in soak. Chlorine emissions are a little bit different. Chlorine is typically not in the crystal structure of a ceramic material. It certainly can be in the binders or in the carbonaceous phase that might be entrained in the kiln. It certainly can be in some of the fuels that you use. So nevertheless, we can detect that pretty easily by X-ray fluorescence. Lower detection limit is about 35 parts per million. So in a couple of samples I looked at that were natural materials containing natural carbon, you can see that there was a little difference here in the chlorine content defined as HCl, and once it's fired, that contains less than that determined by X-ray diffraction. Interestingly, sulfur dioxide and hydrochloric hydrogen chloride, both, as you know, form acids when they mix with water vapor. One of the good ways to know if you've got a problem with HCl or HF is just to look around. Some plants I've seen, the dryer stacks have been completely rusted out. And the plant manager says, "Why is this happening?" Well, you have to tell them. So if you get corrosion on kiln cars or components in the dryer, things happening in the kiln, you'll know that you probably have acid gases. With sulfur dioxide, you'll also know by the nose, because your nose is very sensitive to sulfur dioxide. So it has a bitter smell to it. So if you're walking around on the top of the kiln while it's in operation, you can just smell the sulfur dioxide up on top of the kiln. So it comes from two places: pyrite oxidation. Iron sulfide is pyrite, which is entrained in a lot of natural clays. If these clays come from areas where iron was mined, I find more pyrite in clays from these areas, and so you're going to have the oxidation of pyrite at about 450 degrees C. It's a fairly complex oxidation, and of course, people that make heavy clay products know that they want to get all the pyrite oxidized during firing, otherwise they're going to have some discoloration potential with the product and service. Sulfur dioxide can also come from decomposition of sulfates. Usually sulfates are really undesirable in ceramic products as a presence. Here's a little thermal analysis curve showing the oxidation of pyrite in two distinct steps. And later on, here's the sulfate oxidation, which takes place over a fairly broad range of temperatures. That gives you some insight into how that is emitted. Now I want to talk about metals volatilization. It turns out that many of the metals that are volatilized in firing ceramics come from the transition elements that are on the periodic table of elements. Some of these we know about: arsenic and lead are fairly volatile, that are outside of the transition elements, but nevertheless if you have these elements in your composition, you should at least suspect that you have the potential for metals volatilization. Now, the first time I ever saw this as a university student was when Professor hired me to make some powder compacts of magnesium oxide and pigment grade chromic oxide and fire them. He was studying the kinetics of that reaction in fine powders. And so I would press these compacts. They were small. They were about 2.5 centimeters in diameter and maybe a centimeter in thickness. Put them on the hearth of the kiln, fire them to various temperatures up to 1400 degrees Celsius. And the first thing I noticed was that when the kiln cooled off and I went in and take the little cylinders out of the kiln, I could see a halo of green material around where the pellet was sitting. I couldn't understand that. I thought, this must be surface diffusion of the chromium out onto the hearth of the furnace. Well, it wasn't. It was vaporization of chromium. So I know that now, but didn't know it at the time. I've run into some cases of metals vaporization. I know of one ceramic operation that was injecting zinc into a kiln in order to obtain a certain color on a ceramic product, surface color. And they found that they had zinc emissions from their kiln when there was a stack test. It wasn't any surprise to me because zinc is fairly volatile. In another case, an environmental agency in one part of the country called me up and said, we found zinc in soil samples around a kiln exhaust in a ceramic operation. And they seem to be pretty close to where the stack exhaust is in geometry. I mean, they were pretty close to where the stack was. And toward the property line, there were very little chromium. They said, what's this? And I said, well, that's vaporization of chromium in the kiln. It comes out of the stack. It doesn't go very far because it's really heavy. And so that was metals vaporization. So I've done some work trying to verify that in some very exotic instruments in Europe. And usually you have to be worried about metals vaporization at the temperature is above 1250 degrees Celsius. You can at least begin to think about it. Now, it is true that in some operations, some refractory line vessels like incinerators, if you have metallic chlorides, you'll get metals vaporizations at lower temperatures. Metal halides tend to have fairly high vaporization potential. Then there's volatile organic compounds. So this is a three-dimensional plot. Here's temperature increasing from room temperature going up. And we're looking at the gases evolved within the firing chamber as a function of atomic weight. So this was a mass spectroscopy instrument. And you can see that some things like CO2 we got early on, okay, in firing. Some other things like HF are shown out here. HCl seem to be high all the way along as we're having CO2. That goes with the fact that the carbon was burning and the hydrochloric acid was also coming out at the same time. But you begin to see some more complex molecules being evolved, okay, out here. And these are things that were certainly not present in the ceramic composition, but they are things that are evolved in firing of the ceramic. If we go up to much higher molecular weights in this firing or heating, we begin to see things start showing up at very high molecular weight. It's a mass spectroscopy instrument, so this curve is generated as a function of mass overcharge. But nevertheless, we begin to see other things showing up. And they're identified right here at a couple of different temperatures, a couple of slices of that chart. And some of the things that we see are acetone being generated, toluene, phenol, and xylene. Now, a lot of you will recognize that those are components of solvents that are being emitted in the heating situation, maybe in very small quantities, because this was an extremely sensitive instrument that was being used. Mass spectroscopy is typically not used in stack testing, but these are things that are being emitted in the molecular weight range for acetone, toluene, phenol, and xylene. So nevertheless, this is why regulators can find fragments that are floating around of molecules in your kill atmosphere that they detect as acetone. Is acetone actually there? I can't tell you, but something with that molecular weight is there. Now, on condensable particulate matter, we talked about that, and we believe condensable particulate matter is substances that are liquids that are injected into a stack plume and solidify. Just a story in my experience, the first scrubber on a brick plant in the United States was installed due to stack opacity problems. You could see the stack plume too well. And so when substances were caught in that scrubber, they were found to have condensable particulate matter, which was a complex salt containing ammonia and fluorine. In another instance, I was asked to look at condensable deposit on the exit end of the kiln near the stack that we had accumulated in that kiln. And of course, being a ceramic engineer, the first thing I did is X-ray diffraction. What's in this thing? And so I found some components I expected, like malite, perhaps kyanite, aluminosilicates, cristobalite, fairly high temperature kill. But then I began to see some complex salts that I didn't expect. This was a solid piece that had to be chiseled off the wall of the kiln. A little later on, one of my colleagues did a stack test on the plant. So what you're seeing is fiberglass filter here. You see particulate matter that was retained in the fiberglass, but look at this material that basically looks like glue that has solidified, or taffy, or some material like that on the filter pad. Well, that's the condensable particulate matter that was caught by the filter pad and of course solidified at the end of the experiment. How do you put this in perspective? There's a lot of tabulated data on ceramic plants. Here in the United States, we have the Environmental Protection Agency's publication, the AP-42, Air Pollution Volume 42, which has tabulated data for many, many ceramic plants. I would be sure that that would be available in other parts of the world. AP-42 is available on the internet. Just Google AP-42 and you're going to find it. So to put things in perspective, if people say that living around your ceramic plant is unhealthy, you should say no. They could say, well, you have hydrogen fluoride being generated in your stack plume. You can say, well, there's not enough concentration to create a problem in these fluorine in our toothpaste. Now, I have investigated whether anybody that knew a lot about the development of the ceramic industry had seen hydrogen fluoride poisoning in any individual in the United States. And I know of one particular case. This was before World War II, when the kills were mostly periodic kills. The kill fireman working around a kill became sick. He became sick because the His throat and lungs were irritated by acid burn, and he had to be off of work for a fairly long period of time. Now, with today's kilns, with high drafts and fans moving air around and tall stacks, I don't think that's true at all. I don't think that there's been any situation where human beings have been sick. Now, it is true that some sensitive flowers have been browned or killed because of HF emissions from some ceramic plants, but that's only a minority, only just a few. Less than a handful of plants have had that kind of problem. And so the State Environmental Agency would know that. That's why a lot of people that manufacture ceramic products in the United States put flowers right around the plant office. And if somebody comes up and says the hydrofluoric acid content is dangerous here, we can say, look at the flowers. Flowers are going to die first before it ever affects you. Well, that's a very practical observation anyway. Okay, now let's talk about firing defects. They're usually created by heating or cooling too fast in the kill schedule. Okay, so I did a little bit of quick internet research and found this reference about controlled rate centering or rate controlled centering. One of these gentlemen was a professor, Hayne Palmer, and you can see the abstract there. I found it on the internet, rate control centering, and he proposed rate control centering as a means of designing a firing schedule. And it is, in fact, the way that a lot of people design firing schedules in the past. So whenever there's a change in dimension that is fairly rapid, people will slow down. And that certainly is true, especially with cooling in ceramics that contain quartz or cristobalite. So I wanted to point that out to you. So here's a very brief listing of defects. Variation in kills side to side and top to bottom. Uneven heat distribution. Well, how do you know if you have uneven heat distribution? Well, one way is testing the product itself. It's going to tell you that. And in fact, I've mentioned to you before that I know of one plant in North America that uses ultrasonics or velocity of sound on kill cars as they exit, just a few selected brick positions in a brick plant to tell if the heat distribution is even. Other people use pyrometric products, cones and keys, fire check keys. These are manufactured in the United States by the Orton, O-R-T-O-N Foundation in Columbus, Ohio. They're used to look at when the kill car exits, and you can snatch them off the car and make your observation right there. Other people use traveling thermocouples or some of the systems that attach to a kill car that transmit thermocouple signal to the outside world, so you don't have to fool with all the wires that are traveling down a tunnel kill. So those are the ways that people try to form a uniform distribution of heat within a kill so that all the products see the same heat work. Now we have defects by geometry, and that means they may not meet a size specification. Generally, in this course, we've talked about ceramic products shrinking during firing. That's not always the case. They can undergo expansion reactions. In fact, my first job in the ceramic industry was working in research for a company that made products that underwent expansion reactions in firing. They shrank and they expanded. The net result is they came out of the kill the exact same size that they went in the kill. Okay, there was no net size change. That's really unusual. Sometimes additives are made to ceramic products to cause internal expansion during heating or firing. And sometimes those additives can be used to create specific pore size distributions. Some expansions take place, particularly in clay products, when calcium is added. And that's going to change the pore structure of the ceramics. And that's been a subject of much debate. We can also have warpage, load deformation. These are obvious things. Preheat cracks. Preheat cracks in most of the industries I've worked around are by heating too fast when some volume change takes place, like dehydroxylation. And that will form a crack within the ceramic. Binder burnout can happen. Bloating can happen if there's carbon release or gas release during the time that there is something that seals the pores, like development of glass phase, then the ceramic can bloat, and you will see it immediately. Cooling cracks. Cooling cracks mainly due to quartz in many of the traditional industries. That's on cooling from the kill soak temperature down to the temperature at which quartz inverts, 573 degrees C. So many of the cooling schedules with those products that contain quartz are designed to cool very quickly down to where quartz inverts from beta to alpha and cool very slowly through that transition. That's called the quick cool. I showed you a graph of a quick cool earlier in the course. Of course, the quick cool was invented mainly to get more product throughput in the kill, because the kill is a defined length, and use a quick cool, you can put more product per unit time through the kill. It's also certainly possible to thermal shock the product and cause microcracking within the product in the cooling cycle. We also in this course talked a lot about dunting and delayed dunting. That's making products that contain stress at room temperature. When they're cooled, the cracking may show up fairly quick, or they may show up later. Some of the refractory bricks that I made in my career had stress in them as they were existing at room temperature at the time. The way that I figured that out is I did modular rupture versus temperature. In hot modular rupture, I took the fired specimens and tested them at various temperatures where they were reheated, and I found out the modular rupture went up on heating. Usually you think about the modular rupture going down on heating, particularly wherever we have a glass phase being formed. But the modular rupture went up, and that told me that the product contained stress internally as it existed at room temperature as it was manufactured. Okay, Unit C, a brief unit. Some concluding comments. We started with a simple energy balance in this course. Energy in this little Sankey diagram equals energy into the product and energy being drained off other places. So whatever we supply is the energy to perform work plus the energy losses that occur in firing. It doesn't get any better than that diagram right there. That's why I repeated it. So we had some major themes in the course. We talked about laboratory firings being used to develop firing schedules. That's try it and see what happens, and kind of an iterative process. Let's zero in on the optimum firing schedule by trial and error. Well, that's one way to do it, and that's the way it was done over many years of history of producing ceramics. In the more modern world, since World War II, when we've had instruments to do this, we've had phase diagrams and things like X-ray diffraction, X-ray fluorescence, thermal analysis, thermal dilatometry, and we can link all those to what's happening during firing. So we have a lot more information available, and frankly, since about the late 1900s, 1980, 1990 or thereabouts, we've had computers that are linked to laboratory instruments that control laboratory instruments. So we have real quick access to data, and also the computers have made the instruments much more accurate. So now we have a lot more information than just trial and error to design firing schedules. Along the way, we said kilns were enclosures where we concentrate the heat to do the heat work in manufacturing ceramics. So there's our energy balance. The heat required by the load plus the heat of storage and the heat of losses. We talked a fair amount about fuel safety. I urge you to become very, very aware of all safety aspects of handling fuels and relighting kilns, topics of this particular nature. Fuel spills, for example. Now we use furnace apps to answer what-if questions. These were used to minimize energy cost by using predictive processes. They weren't exactly accurate, but well, golly, no one wants to build a kiln with not enough firepower in it, not enough energy release. So maybe these things help you understand that you may need more energy than you can theoretically calculate. So that's been the course on firing of ceramics. There's a lot more for you to know. There are things that we did not cover in this course that are a lot of details that you need to know about. Here's one: interchangeability of fuels. You're going to put a backup fuel through the same burners as your primary fuel. What kind of backup fuel do you need? And what are the rates of backup fuel consumption compared to your primary fuel? That's called Willoughby Index. We didn't dwell on that. It's like a lot of other little details that we really didn't have time for. So I urge you to contact the thieves people and get the North American Combustion Handbooks and make them your best friend if you're working in combustion, because those two volumes have a lot of information. I also urge you to keep your eye out for kiln simulation programs that may be more applicable to what you're doing. So if you work at it, you can become very good at what you do. And so now I want to pause a minute and offer you my best wishes with some concluding comments. I've known a lot of people during my career as a ceramic engineer. I'm obviously an old guy. You can see the blue tint in my glasses. I have computer glasses on, which reduce the transmission of certain wavelengths of light, trying to make my eyes a little better. You've noticed me squinting at the screen, trying to read from the screen because of my age and some of my eye problems. You've noticed me fumbling with speaking sometimes. You've noticed me making arithmetic mistakes, perhaps. I've done the best I can. It's really difficult when you don't have a live audience in the course, because you can always tell how you're doing. Students will laugh at you, okay, if you make a mistake, and they'll point out your mistakes. So also, with live students, can tell how the student is progressing through the course. So I want you to know that you have that time available for contacting me with questions. Now I want to wish you well. Now, I asked my old professor, Professor Gilbert Robinson, why he became a ceramic engineer. He was a Navy veteran of World War II, really smart guy, a good guy, and he said, well, I just thought that ceramic engineers made products that were usable by society. They were good products, and I was interested in them. Well, I was expecting a professor to give a more dignified answer, like, well, the science really enthralled me. I was really impressed with the chemistry and physics of manufacturing ceramic products. That's not what he said. He just said, I thought it was a useful career. Further, I've known a lot of people along my journey through ceramic engineering. I've known brick manufacturers that got a thrill by riding around their community, and they could point out and say, I made the bricks in that house. Being thrilled that they made something useful for society that was beautiful and made them feel self-worth that they made something useful. I've known people at all levels, plant supervisors, laboratory technicians, who were very competent at what they did. And these people always tried to get better at what they did. And some of these production supervisors, meaning a unit operation in manufacturing, knew more than me. Well, that's okay. Teach me something then. I'll get smarter with time. So I urge you to continue to progress along your journey in ceramic manufacturing. One thing that comes to mind is numbers. When I first was a university student, of course, they make you do problems in engineering, infinite number of problems. And what you don't know when you're a university student is that you're going to have problems to solve all your career. So that's why we're doing them now in college, is get you used to solving problems. But sometimes I didn't like numbers. I didn't like dealing with numbers. And especially when I became a professor, I emphasized looking at numbers. Look at the variation in physical properties within materials, looking at what you're creating in a firing process. Numbers are the way that ceramic materials talk to you. Now in my career, I also had a specialization in microscopy, so I got to look inside the ceramic as well as outside the ceramic. So that's why I design courses trying to tie together chemistry with X-ray fluorescence, with mineralogy, with X-ray diffraction, with thermal analysis like thermal dilatometry. Tie everything together in courses, and that's what I've tried to introduce you to here today. So I wish you very well in your journey in ceramics. Keep trying to be better every day. Keep trying to learn, and you'll make very useful products for society and have a great career and a great life. Thanks for letting me host this course. I bid you goodbye.